Hello, geometry students. It's day 4 of Unit 5, and we're talking about something called the mean proportional. So the mean proportional, what that is talking about, when it says you have a geometric mean between two numbers, it's the number that creates a proportion and makes the parts equal. So what I mean by that is if I let x represent the geometric mean, all right, what that means is that I can say that 2 is to x as x is to 8. It's saying what value can you put here and here that would balance and create a true proportion. So if we solve, we would cross multiply. This would give us x squared. This would give me 2 times 8 or 16. And then when you take the square root, technically it's plus or minus, but 4. All right. And so if you think about checking that, 2 over 4 is equal to 4 over 8. Well, yeah, this comes down to be 0.5 or 1/2, and so does that, right? And same thing would be true if I put a -4 here and a -4 there. It would just be -0.5 equal to -0.5. So that's what it means when you talk about a value being a mean proportional between these other two values. So if you try that again, for number 4, we're going to let x be the value again. We're saying 4 is to what number as what number is to 9. All right, if I cross multiply, we get x squared, we get 36. So far, these are coming out nice and pretty, so we would get plus or minus 6. And so that means 4 is to 6 as 6 is to 9. Both of those, if you divide, come out to be 2/3 or 0.6 repeating, whichever way you want to think of it. They don't always come out that nice and neat. So when you look at one like number 3, if we say 3 is to what number, as to that same number would be to 8. Well, here we would still get the x squared, but then when we get 24, it's not a perfect square. So when you go to take the square root, the best you can do is just simplify it. So it's still going to be a little plus or minus. You don't want to forget that part. But then you'd have to break it into a perfect square, and then times whatever is left over here. So in this case, the perfect square that nicely goes into 24 would be 4, and then our leftover would be times 6. So then I take the square root of the part that I can. That'll give me 2. So that's this piece of it, and then I'm stuck with that radical 6. Could you change it to a decimal? Technically, yes, but we don't ever put decimals in ratios like that, so we would just keep it as a nice exact value like that, right? And then you can try one more. So 5 is to x, and then as x is to 9. So what you're probably starting to notice is every time the mean proportional is just that value squared and then equals the product of the other two. So 5 times 9 or 45. Right? If you think about this one, 9 was a perfect square, or I should say is a perfect square. So it's going to break right back down into that. So it'll be plus or minus. Square root of this is 3, and then I keep that radical 5. So that would be the value. That's the mean proportional. And now if you're looking at it and thinking like, can I actually show that? Technically, if I did 5 is to 3 radical 5 as 3 radical 5 is to 9, it's not very easy to simplify, but you could grab your calculator and divide each and kind of convince yourself. So what I mean by that is if I go to, let's see, maybe I'll use my alpha y equals here. If I do 5 and then divide it, 5 and divide it by 3 radical 5, that gives me this decimal of approximately 0.475, and it keeps going. The idea is that this should give me the same value. So if I do 3 radical 5 and then I divide that by 9, there's that exact same value, right? So approximately equal to this. So even if the answer looks weird, it can still be the mean that's proportional between those other two values. All right. So why do we bring this up? Well, you're going to see some properties in similar triangles where this becomes something that we can use to solve for some missing side lengths. Now, before we get there, it's saying in the geometry of the mean proportional. Well, if you have a right triangle ABC where you have an altitude CD drawn to the hypotenuse. So if AB is the hypotenuse, that means this is my right angle up here. This is my altitude right here. And what we should know and altitude. We're not going to do a formal proof here, but I want you to kind of think. Altitude means that I've got perpendicular lines, which means we've got right angles. So we'll just kind of think it out the way that we would a proof. So little right angles right there. The reason I point that out is it says show that triangle ADC, so this is ADC right here, is similar to ACB. All right, let's go with, we'll kind of color code these here. ACB, I'll get my highlighter for that one. So that's the big triangle right there. My blue is the one on the left. And then as always, I got my red pen sitting here. And then CDB. So CDB. So you have 3 triangles, essentially, when you draw the altitude in, going from the right angle down to the hypotenuse. And what we're saying is, can we show, or should we do need to show, that they are all similar? And so to show similar, we know the way to do that. That's by angle similarity. Well, since we're doing this kind of informally, we don't need to do a fancy 2-column proof. What I'd want you to look at is all 3 of those triangles right now, right, have a right angle. So right there, that would be one pair of angles between any of the triangles that you look at. Okay, where do you get the other angle? All right, well, if you take a look at this, if I look at, let's say, like the little blue triangle and the yellow one, if they overlap, that should be code for thinking about reflexive property. And what do those 2 triangles share? Well, my little blue triangle and my yellow triangle, they both share that bottom left corner of angle A. So if this was a formal proof, I'd say, A is congruent to A, and I'd have a little reflexive property. So between these 2, that's where my angle would be. It would be angle A that they share, and then the right angle. And so right there, I've just shown that the blue triangle and the yellow triangle would be similar. And now we could play the same game with the big yellow triangle and then the red triangle. They overlap over here at angle B. So between these 2, they both have angle B by reflexive, and they both have a right angle. So that would be how we would actually show angle similarity there. And then I can make that same argument to say that, well, if these 2 are similar and these 2 are similar, then all 3 would be similar, sort of by a transitive property, right? So when it's saying show it, we're really kind of, talking our way through it. But what the big takeaway here is I want to focus on the first triangle. So write this down with me. ADC being similar to the red triangle, the last one, CDB. Now think about the proofs that we did yesterday. We showed proportional parts, right? If those are similar triangles, then the parts that are proportional that I want to look at for today's lesson would be, I can say AD is to DC. So AD is to DC. So look at the order where those are. First 2 letters, last 2 letters. Same thing over here as CD is to DB. All right. That has to be true because similar triangles implies that corresponding sides are proportional. All right. Well, if I take a look at the picture, AD is this segment right here. And then to DC, that's this guy, is to, well, CD. CD is the same as DC. So these guys are the same right here. This segment is to DB, this one over here. So what that really means is what we're showing is that segment, CD or DC, call it what you will, is the mean proportional between AD and DB. So DC is the mean proportional between AD and DB. And so what that means is when you kind of strip down the rest of the picture, you can kind of create a little rule of what we just looked at there. This length right here, I think on the next page we call A. This length right here we call B. And then I believe the length in between we call X. So I can kind of take all like the notation out of it there and just say that A is to X as X is to B. And now you can see that mean proportional setup, and you know why we did that first page. All right, so let's take it on over and let's use that rule on the next page to solve for some missing parts of the triangles. So right here, write that rule down one more time. We're going to say that A is to X. So that little segment is to the altitude, as the altitude is to the other little segment here. X is to B. And when I see you in class, I'll show you like a little fun trick to remember that. Right? But now if we actually use it to set up the proportion, I'm going to slide on up here. We can say that 6 is to X as, come back down, X is to 24. So as long as you have an altitude drawn in a right triangle, which we do here because this is a right angle, that's a right angle, then that proportion should hold true. So now when we go to solve, X squared here, 6 times 24, well, feel free to grab a calculator. I've got mine sitting right next to me. So I can do 6 times 24, and I get 144. Oh, and that works out so nice and pretty because the square root of that is going to be plus or minus 12. Now, when we take it into the triangles, we've talked about this before. I wouldn't make that length negative. So at this point, you can ditch the negative part and just keep that positive answer of 12. Now, does it necessarily look drawn to scale? I don't know, but don't worry about that piece of it. The idea is that if it was actually drawn to scale, that length would have to be 12 there. So let's try it one more time. We've got 4 is to X, and then as X is to 5. All right, once you've got it set up, it's nice and easy to solve. X squared, and then 4 times 5, that's going to give us 20. So you know right now this isn't going to be quite as pretty as the last one, but it doesn't mean that we can't do it. Take the square root, break it into perfect square times the leftover. So in this case, 4 would be a nice perfect square times 5, because that's where it came from in the first place. And so then 2 radical 5 would be the answer for the height there. All right. Some of them are going to look a little bit different where we've got more X's going on. And so on this one, I like this one because when we go to set this up, the X isn't the altitude. The X is this piece over here. So make sure you're using the diagram appropriately. So X is to the altitude of 12, as the altitude 12 is to X plus 7. All right, when we go to solve this one, we're going to cross multiply and get X times X plus 7, and then 12 times 12. So that's going to give us 12 squared, or 144. You can put that in there. On this side, we're going to distribute. So X squared plus 7X. And now we saw a couple of these a few days ago in the notes. We need to get it equal to 0 so that we can factor. Right? All that algebra 1 coming right back at you here. So subtract, the 144 over to get it equal to 0. And then we are looking for two factors that add to 7, multiply to 144. As a little reminder, you can always go into your y equals, get rid of whatever's in there, and we can do 144 divided by x to look for those factors. So if I go to my table now, I can see like 1 times 144, 2 times 72, 3 and 48, 4 and 36. So I'm looking for where they're going to have a sum or difference of 7. So 8 and 18 is getting closer. There we go. 9 and 16. So if we do a positive 16 and then a negative 9, that'll add up to the 7 that we want right there, but multiply to give us negative 144. All right. When we go to solve, I'm almost out of space. I know that when I set it equal to 0, it's going to flip the sign. So this will give me negative 16. This will produce positive 9. And I do not want to keep any negative answers if x is an actual length here. So get rid of that. So x equals 9 would be our solution here. And then if you want to check it, you certainly could. That would make this 9. It'll actually make that piece positive 16. And then we could set it up to show that it works. All right, there are a few more on the next page, but I think we will save those to talk about together, especially because you have to draw them on your own, and it'll be nice to look at these ones together in class. So write yourself a little note that will recap these last two together and make sure that you've answered the video questions. Thanks, guys.